Oh, hi. Today we will talk about the real and reactive powers of synchronous machines. So in the last lecture we talked about the real power in a synchronous machine, which was equal to, again, this is valid for any three-phase AC system, so voltage times current times the power factor. And what we defined, just as a quick reminder, is like we had Vt here, then we have the Ia, then this was JXS Ia, and this was EF. Let me write all those things. So this was Vt, this was Ia, so this is our power factor angle, this is our load angle, this is EF, this is JXS Ia. So the idea was, geometrically that distance is equal to XS Ia times cos theta. At the same time, that is equal to EF times sine delta. So we were using, that equation to write, instead of that one, we were writing EF sine delta divided by XS, and by that way we could find the power in a synchronous machines in terms of the terminal voltage and field induced voltage. So actually it was same for any AC system. So if there's any AC system, a lossless AC system like with a inductance, so the power always flows from the leading side to the lagging side, and the magnitude has no importance in terms of the power flow. So what about the, this is the real power, and what about the reactive power? So let's do a similar approach, like first geometrically, then I will derive the same thing more formally using the mathematical phasors and that kind of things. So anyway, so in real power was Vt Ia cos theta, and similarly reactive power, if you remember from previous years, it was Vt times Ia times sine theta, right? So if it is at unity power factor, the theta will be 0 and there will be no reactive power if the power factor is 0. Actually, power factor is the definition of real power to the overall apparent power. Anyway, so how we can obtain that relation? So first let me draw the same vector here, right? So again, this will be my Vt, where I draw it so many times. So this is Ia theta, same color code as before. So that will be JXS, JXS Ia vector, and this was the EF vector, and this is my load angle, and of course I know that one is 90 degrees. So where is Ia sine delta? What is that one? So in order to do that, I will use the similar trick as before. So I can write that one, and if this is delta, this is 90 minus delta. So this is, as well as this is also, sorry, not delta, theta. So this is theta. So we know that equation, so that distance over here was XS magnitude wise Ia times cos theta, and that one, in this one, so that distance over here, okay, so similarly it is XS times Ia times sine theta. So I have that distance in terms of the armature current. So how can I represent that distance in an alternative way? So I can try to calculate that distance. Okay, let me draw it over here. So what about that distance? So that distance is equal to EF magnitude wise, okay, this is not vector, this is just geometric. So this was sine delta, and all that distance is like cosine delta. So I can write, okay, I can write EF, again magnitude wise, EF times cos, okay, cosine delta minus, I mean this, that distance minus Vt, okay, minus Vt is equal to that distance, right? XS times IA times sine delta, sorry, sine theta. So the thing that I need to do is, instead of that one, so I can rewrite that equation IA sine theta is equal to EF, right, slightly larger, cos delta minus Vt divided by XS, right? So I can write these two equations together. So I can write Q, okay, reactive power is equal to 3 times Vt times EF cos delta minus Vt divided by XS. So that is the, you know, geometrical derivation for reactive power. So let me, you know, that is how we derive it, and let me write it here. So what does it mean? What does it mean? So it means, again, let's have a look at the direction. Again, this is positive, positive, that one is positive. So if, okay, if EF times cos delta is larger than Vt magnitude wise, okay, I mean that term is now larger than 0, then Q is larger than 0, or if, when similarly EF cos delta is smaller than Vt, then that means Q is less than 0. So the direction of Q, okay, the direction of Q is mainly, you know, defined by if the projection of that EF over Vt is larger than that one, if it is coming here again in a remember lagging power factor like that, so that means that distance is larger than 0, so I have a larger Q. So let's have a look at a similar case. Let's have a look at leading power factor, okay. So let me, so we will have more space. Let me try to draw it here. So that will be again our Vt, right? Then in this case, let's use a leading power factor. So this is AA. So now we have leading power factor, and again now that thing is going to be vertical 90 degrees over that one, right? So this will be again rating the things, but IA here and EF is here. That is our load angle. So as you can see, in the previous case, so EF cosine delta minus Vt, or in other words, that one, or that projection over Vt is longer or has a bigger magnitude than Vt, so Q was larger than 0. However, in this case, if you look at the projection, okay, so that is our projection over here. So EF cos delta is here minus VT, then that results in a negative result, negative value. So that means in that case Q is less than 0. I will show you a couple of more examples, but here that means if the magnitude of EF is larger, then reactive power tends to get positive. But if it is smaller, or to be more accurate, if the projection of EF magnitude is smaller than VT, then reactive power gets smaller. Okay, so that is geometrical derivation. So we will I will give us a couple of more examples in the next slides. So but before that, let's try to derive it formally. Okay, all that power and Q relations also can be derived from the conjugate of vectors and that kind of mathematical relations. It's usually more difficult, but just as the sake of completeness, let's do that. Okay, so for that, what I'm going to write is let's start from a formal definition. So S is the power is Vt times Ia conjugate. All right, so normally if you have any machine or motor, then if you know the Vt and Ia vectors, so you can calculate the all power, real power and reactive power using that one. Remember, the real part gives you the real power, and imaginary parts give you the reactive power, but we can derive both of them using that equation. Right, so let's try to write that one. So we have 3 Vt. Okay, what about Ia? So what about Ia? So let me before moving on that one, again let me draw a phasor and for definitions, bothering with the color for now. So this is Vt, this is delta, this is XS Ia or magnitude wise, and again that distance was theta, and this is EF, right? So that means, let me write J here. So if I have EF, so that is fixed, and if Vt is fixed, I can define the Ia vector like the difference between two voltage vectors divided by Jxs, right? So I can write that one as like Ia vector wise, that is equal to EF minus Vt vector, right, divided by Jxs. So how can I write that one? Ia vector, so EF again can be, Vt is in the real part, so EF can be separated in the two domains. So the first one is like EF times like cosine delta, that is the real part, right? Write it here, plus J sine delta. So that defines the EF vector. So EF cos delta is the projection over x-axis, and J sine delta is over y-axis. Okay, minus Vt. I mean, this is not the vector, but the real the magnitude, because it's in the horizontal axis, and it is divided by Jxs. So instead of Ia, I'm going to write that equation now. S is equal to 3 Vt, okay, EF cos delta plus J sine delta divided by Jxs minus Vt, and that will be again the conjugate. So let's try to write that down. Okay, So here the real part, I mean, is divided by jxs. So that part, EF times J sine delta divided by JXJ cancel each other. So what I have is 3 VT, okay, times EF times sine, write it larger. Right. So 3 VT EF, so that one and that one, J's cancel each other, sine delta divided by xs, so that is the real part of that equation, okay, plus then I have normally something divided by j, I can multiply it by another j, so it becomes j here, and it's minus 1, j square is minus 1, so it becomes minus j something, but I need to take the conjugate, so it becomes positive, so you can derive it yourself. So I will just put the j here, so I have 3 vt times, okay, ef times this time I have cosine delta, right? Then I have minus, let me write 3 something here, minus vt square, or let me write it like that, just minus vt divided by xs, right? So again, if you look at that equation, if you remember it from the earlier week, so it is 3 VTEF sine delta divided by xs, so this is real power, that is p, and actually that is exactly the same equation that we derived here, so that part is the reactive power, that is q. So technically, you know, you can start from that equation, you can get the IA, and you can derive those two vectors, so no problem there. So let's continue. I mean, again, from what we see here, again, the direction of the real power is determined by the polarity of load angle, because sine delta is the same, has the same polarity with delta. However, here it is determined by the polarity of EF cos delta minus VT, right? So let's summarize those things, and again I will show you a couple of more examples to understand that concept better. So for real power, actually it has nothing to do with the magnitudes of VT and EF. So real power flows from leading side to lagging side, okay, and reactive power actually flows from overexcited. So what does it mean? So that means if it is overexcited, so let me write it here, so EF gets larger with IF, field current. Okay, so that means if it is overexcited, so it means if the field current is large enough, then the magnitude of EF will be large enough, so that will result in, you know, some reactive power flow from overexcited. So in other words, IF is large, okay, to underexcited side. And lagging power factor generates, again I will show you a couple of phasor examples. So lagging power factor generator supplies Q, reactive power, and lagging power factor motor absorbs Q. So that is, you know, usually a confusing concept. Like real power, it is easier to understand, where the real power, again, if it is working as a generator, then it supplies real power. If it is working as a motor, it consumes real power. But with the reactive power, it's usually quite confusing. So let me show you a couple of examples for that. So for that, let me draw a simple case like 1 generator is connected to a motor, right? So here we have the generator. So I will show the field winding as like EF generator, right? So then you have XS generator. So this is our terminal voltage for both the motor and the generator, and then we have IA. So this is generator side. So then I have the identical machine, same parameters, but one of them is working as a generator and the other one is working as a motor, right? So let me draw it here. So it becomes EF motor, and let's say this is XSM. So this is the VT, same terminal voltage for both the generator and the motor, and obviously the same current gets into these ones. So that side is working as a motor. So yes, power flows from left to right. So from real power flows from generator side to the motor side, and of course in reality they have those shafts, and you have the one of them is using mechanical energy to generate electricity, and the other one is using electrical energy to generate mechanical output. Okay, so they usually have the input and output shafts, but I'm not showing it here. So now let's have a look at the phasors. Okay, so at first let's have a look at for the unity power factor. So what happens if I operate both of them? So actually you measure the power factor from machine terminals, so that means VT and IA, they will be in phase. So first let's draw the generator. Okay, for generator what I have is I have the VT here, right? So I have, let me not use that one. Oh, sorry. Okay, so not use that one. Let's say this is our IA, and that means I have JXS IA, and that will be EF here, and that is my load angle. So this is our VT, this is our IA. So this is the generator side. So let me draw the motor side. For the same operating condition for the unity power factor, let me draw the motor, and for motor I will have the same VT, okay, same IA here, and now it is not like VT plus JXSA is equal to EF, but it will be minus, remember, so that will be that direction is minus JXS IA, right? Or it depends on how you define the relations, but anyway, so this is my EF and this is my load angle. And of course from here, what you can see from here is EF actually leads the terminal voltage, so it is supplying real power, and here EF lags VT, so it is consuming real power. So from here, the power direction, let me draw it here. So it is that's direction, right? So that means power is flowing in that direction, right? Again, that one using power. So that means generates P, obviously, and consumes P. What about Q? So let's have a look at the Q. So what is Q at that point? So it is again like operating at unity power factor. So again, you can just go up, those things. Again, the reactive power is sine theta, and if it is working at unity power factor, all S is equal to P, so there is no Q in the system, right? So again, you can see it from here. Let's have a look at EF cos delta minus VT. So what is EF cos delta? So EF cos delta here, that is equal to VT. If you make EF cos delta minus VT, that is 0. That's the same thing here. So that means Q is 0. Obviously, it is unity power factor, and it is Q is equal to 0 for the unity power factor condition. So let's draw the same thing, not for unity power factor, but for lagging power factor, right? So I'm going to draw that one, draw the VT. So this is VT, and now IA is working in the lagging power factor, and as a result, you will have that one, J XS IA, and you have EF here. So now let's look at the real power. Still EF is ahead of VT, so I can say the power, again, it is generating power, and power direction is from left to right. Okay, and let's have a look at the lagging power factor, and let's look at the reactive power. So in this way, so EF, okay, actually is larger than that value. Okay, so that means if you just go back, so it is, for that one, EF cos delta minus VT. Now that one is larger than 0, so it is 3 VT. That's positive, that's positive. Again, you can see it from here. This is EF cos delta minus VT. It is that area, so Q is larger than 0, so you can say this one is also supplies power. Sorry, supplies reactive power, supplies Q. So let's have a look at the same condition, because actually now they are working to the same terminal voltage and it's the same current. So the motor should operate as in the leading power factor as well. So in that case, let me draw it again. So we will have VT. Okay, that's our VT. That is our current. That is IA, right? So now let's draw that one, but it will not be coming in that direction. Remember, because of convention, it will be in that direction. So it's minus J XS IA, right? So I can draw EF to here, and this is my delta. And as you can see, I mean, it is still lagging. EF is lagging VT, so you can say it is consumes P, so power flow. Again, it is using some power. It's all for those cases. And let's look at that magnitude wise. So now, I mean, let me write those things if you don't get confused. So this is EFG, this is EFM, this is EFG, this is EFM. So you start with a large voltage here. So, and once you measure that voltage, that VT is smaller and it is lagging that one. Then you apply that VT to motor, then you end up with an even smaller EFM, that is that voltage, and that one is lagging that VT. So power first flows from here to here and from there to there. Actually, what you can do, I mean, if you are if you understand what we talked in the previous video, you can just combine these two inductances and it becomes just like a single system, right? So you can just do that. Anyway, for that one, what you can see, EFM cos delta is now smaller than VT. So if you calculate that value, you will see that will be less than 0. Okay, so here in this one it is Q is less than 0. So this one's actually it consumes, okay, consumes reactive power. So that is why in the previous case, or actually maybe we shouldn't write consume, because it's not really consumption, it is not dissipation. Maybe we should say absorb. Okay, so again from here, lagging power factor generator supplies Q and lagging power factor motor absorbs Q, right? So that is what does it mean. So for the sake of completeness, let's do the leading power factor. So I copied the same graphics here. So let's do the same thing for leading power factor. So for generator, try to plot it here. So that is my VT, and that is my IA, it is my theta, and you can it's a XS IA, and you will find EFG vector here. That is your load angle, right? So in this case, let me draw the motor then. Same VT, okay, same IA. But now the direction changes, so you will end up somewhere here. Yeah, so that is that. So still make it here. So still, as you can see, EFG actually leads VT, so supplies, it is still supplies power. Okay, so the power direction is still that one. But in this case, EFG cos delta is less than VT. So that means Q in this one is less than 0. So that means this one absorbs Q. However, if you look at that one, again, you know, EF lags VT. So that means that is consumes real power. So real power is coming from that side to that one. But EF cos delta minus VT is that distance now. That one is larger. So that is Q is larger than 0, and that one supplies reactive power. So in this example, power, let me write like that, real power flows, that one. So this is motor, this is generator. So real power flows from generator to motor. But if you look at the reactive power, this is Q. Reactive power actually flows from motor to generator. Right, so let's do a quick review. So if you are both working at unity power factor, then power again flows from generator to motor as always, and in unity power factor there is no reactive power. If generator is operating in the lagging power factor, then the reactive power also flows from generator to motor. However, if you are looking at the leading power factor, then this time real power flows from generator to motor, as in the previous case, but reactive power actually in this case flows from motor to generator, right? So again, if you just look at that one, I mean in this case, like if you just look at the magnitudes, so EFG, I mean compared to EFM, so it is smaller in magnitude, but it still sends some real power, right? So again, for the direction of power, the magnitude of EF doesn't make any difference. However, for the reactive power, it flows from overexcited side to underexcited side. So overexcited side means IF is increased. So increasing IF means increasing the magnitude of EF, and that means the ones with the larger magnitude of EF supplies reactive power. In this case, it is motor side. I mean, look at the magnitudes of the green vectors. So the motor has a larger magnitude than the generator, so that one is supplying reactive power. However, if you look at the lagging power factor case, this time the magnitude of EF on the generator side is larger than the motor case. So in this one, overexcited side is the generator side and underexcited side is the motor side. Okay, so you try to make those things. Cool. So I mean in general, the important thing is for the real, I think real power flow is more important to understand. So the direction of the real power flow has nothing to do with the magnitudes of those V1, VT or EF. So that is really important. And for reactive power, however, the magnitudes becomes more important. So here again, like this is the generator, this is the motor, the same things that we discussed. So this, in those cases, it supplies reactive power. Generator is working at the lagging power factor. So once it is working at the lagging power factor, produce P, produce Q. If it is working in the leading power factor, generator produces P but consumes Q. However, in the motor, if it is working at the lagging power factor, it means it is consuming power and it is supplying reactive power, right? With the leading power factor. With the lagging power factor, it still consumes P and absorbs Q. Okay, so hopefully it will be clear once we saw a couple of numeric examples. Okay, thank you.